Today we're going to talk about parametric equations. Earlier, we've talked about equations written in the form in terms of x and y coordinate, in rectangular coordinate system. We've seen rectangular equations, but today we're going to talk about parametric equations. Parametric equations, one wide application of parametric equations is the two-dimensional motion. When we throw an object in the air, the horizontal velocity and the vertical velocity are independent of each other. They both depend on the time t. So we represent the x using inducing another variable. Both x and y depend on another variable, t or t square or theta square plus 1, any other variable that both x and y depend on. We can represent x and y using those functions. Then those equations are called parametric equations, where we represent x and y as a function of t or as a function of theta or a function of any other variable. So x is equal to f of t and y is equal to g of t. This is the called set of parametric equations, where t is called the parameter. The set of points x, y obtained as t varies over the interval I is called the graph of the parametric equation. In the case of parametric equation, we are also given, the direction matters too. Direction of the curve matters as well. Parameter doesn't have to be just t. It can be theta. It could be t squared, theta plus 1, t squared plus 2, or any other variable that both x and y depend on. That would be an example of parametric equation. Here's x equals 24 root 2 times t, and y is equal to negative 16 t squared plus 24 root 2 times t. Both x and y depend on the variable t, and that would be a parametric equation. The path does have a direction when we plot or graph the parametric equations. So here, sketch the curve described by the parametric equation. We're going to sketch the curve x equals t squared minus 4, y is equal to t over 2 between negative 2 and 3t. So here, what we're going to do is, we're going to start with making a table for the variable t and find out the corresponding values of x and y. So t starts from negative 2, goes up to 3. Negative 2, negative 1, 0, 1, 2, 3. You don't have to pick all the points. My domain was pretty small, so I picked all the integers in between, but we can skip the points if you have a wide interval. So when t is negative 2, the x is going to be 0, y is going to be negative 1. Negative 2 over 2 is negative 1. When t is negative 1, x will be negative 3, y will be negative half. When t is 0, x is negative 4, y is 0. When t is 1, x is negative 3, y is 1 half. When t is 2, x is 0, and y is 1. When t is 3, x is 5, y will be 1.53 halves. Okay, so now we're going to start plotting this curve, starting the point 0, negative 1. It's over here. X is 0, y negative 1. X is negative 3, y is negative half. So that would be about here. X is negative 3, y is negative half. And then x is 0, y is negative 4. That would be x is 0, y is negative 4. Okay, x is 0, y is, oh no, x is negative 4, y is 0. Okay, so we had the next point here, x is negative 4, y is 0, about here, or maybe a little bit closer. And then the next plot is x is negative 3, y is half. X is negative 3, y is half. X is 0, y is 1, x is 5, y is 1.5. So that would be about here. So this is my curve in this case, and I must draw the arrows in the direction it's moving. So this is a graph of a parametric equation. Note, sometimes it happens that two different sets of parameters will give you the same graph. So go ahead and plot this equation, and you will get the same graph as the previous one. And here the t goes from negative 1 to 3 halves. So more than one, same graph can be represented by more than one parametric equation. Now we're going to talk about eliminating the parameter. What if you don't want to look at the parametric equation in terms of parameters, want to come back to rectangular coordinate system? For that, we will eliminate the t. We will represent or express t the variable t in terms of x or y, whatever is easier, and plug that into the other equation. So here x is equal to t squared plus t, y is equal to 2t minus 1. So eliminate t from y. In this case, it's easier to eliminate from y. Eliminate or express t in terms of y. That's what we're going to do. Start by express t in terms of y. Express t in terms of y. Y is equal to 2t minus 1. Y minus 1 is 2t. T is equal to y minus 1 over 2. T equals y minus 1 over 2. Okay, t is equal to y minus 1 over 2. Now we're going to substitute this t into the other part of the equation, in the x part. X is equal to t squared plus t, so I'm going to replace the t by x is equal to y minus 1 over 2 squared plus y minus 1 over 2. Now we're going to go ahead and simplify it. Open up the bags. Y squared minus 2y plus 1 over 4 plus y minus 1 over 2. This will leave me with x equals, we can multiply numerator and denominator with the 2 here, y squared negative 2y minus 2y minus 2 we will have here, y squared plus, it's going to be y plus 1. Okay, fix it please, y plus 1. That would make it a positive and a positive here. Y squared plus 2y, which is plus 4y, y squared plus 4y, y squared plus 4y, 1 plus 2 plus 3, y squared plus 4y plus 3. So that turns out to be, we can say x is equal to y squared over 4 plus y plus 3 over 4. And that's the equation in terms of x and y, and we had the parametric equation given. So our goal is to eliminate the parameter t and then express the equation in terms of x and y, adjusting the domain after eliminating the parameter. So once we eliminate the parameter, we want to look at where the function is defined as well. So here we're given our equation in terms of x. Both x and y depend on the variable t, and t is greater than negative 1. That means I can pick any values greater than negative 1 in this case. So let's go ahead and eliminate the variable t. So which one is easier? So we're given x is equal to 1 over square root of t plus 1. And from here we can say x square root of t plus 1 is equal to 1 over x. Go ahead and square both sides. Square root of t plus 1, oh no more square root when we square both sides. T plus 1 is equal to 1 over x squared. T is equal to 1 over x squared minus 1. So here we isolate the variable t from 1, either x or y, whatever is easier. Now I'm going to plug this into the other equation. So plug in y. So I have y is equal to t over t plus 1. Y is equal to 1 over x squared minus 1 over 1 over x squared minus 1 plus 1. Okay, denominator. These are going to be gone. And that would be y is equal to 1 x squared in the denominator, 1 minus x squared in the numerator, 1 minus x squared over x squared over 1 over x squared. So we can cancel this and we'll be left with y is equal to 1 minus x squared. So y is equal to 1 minus x squared. So this is my new equation. This is in the rectangular form, not in the parametric form. Here x and y don't depend on the variable t. In the parametric form, equivalent parametric form, x and y depend on the t. For the domain for this equation, think about where is this equation defined. For 1 minus x squared, this is defined for all x values, no matter what the x value you have. So this is defined for all x. Any x negative infinity or positive infinity, this function is defined for all the x values. Now we're going to talk about angles as parameters. What if your parameter is not the variable t, not the variable t plus 1, but instead it is, it's not the variable t, but it's an angle theta. Okay. Now we're going to use trigonometry to eliminate the parameter. We're going to see some examples. Trigonometry to eliminate the parameter. So x is equal to 3 cos theta, y is equal to 4 sin theta. Theta goes from 0 to 2 pi. We also want to graph it, but before that, let's go ahead and eliminate the parameter and find the corresponding rectangular equation. What do you think this equation is? What does it look like? Is it a line? Is it a parabola? What is this equation? The previous one we can see that is a parabola equation in the previous one, parametric equation that was given to me. But this one, let's go ahead and use trigonometry. So I can say x is equal to 3 cos theta means x over 3 is equal to cosine theta. And y is equal to 4 sine theta means y over 4 equals sine theta. Once you have cos theta and sine theta alone, it is a lot easier because we know cos squared theta plus sine squared theta is equal to 1. We're going to use the Pythagorean identity here. Cos theta is x over 3, sine theta is y over 4 equals 1. X squared over 9 plus y squared over 16 is equal to 1. And that looks like it's going to be an ellipse. This is an ellipse. So this is equation of an ellipse. Okay, now if I were to graph it, let me go ahead and plot theta corresponding x and y. So we can pick theta from 0 to 2 pi. We can pick any values we want, 0, pi over 4, pi over 2, pi, as many as you want. When x is 0, when theta is 0, x is going to be 3 cosine theta, 3 cos 0, that would be 3. Y would be 4 sine theta, y is going to equal 0. When we have pi over 4, this is going to be 3 over root 2, and that's going to be 4 over root 2. And when theta is pi over 2, cosine of pi over 2 is 0, sine, that would be a 4. So use this technique and go ahead and plot these points, and you would be able to see it is going to be when x is 3, y is 0, x is 0, y is 4. So it is going to be an ellipse that looks like this. Starting from the theta 0, here is the direction we were moving in. 0, 3, pi over 4, yeah, that's the ellipse equation. Again, we are given x equals cos t, y equals 2 sine t. Let's see what kind of equation is this. I already have the x alone. That was cosine t. But y is not alone. So from here I can say y over 2 is equal to sine t. So x squared plus sine squared theta plus cos squared theta equals sine squared theta plus cos squared. Let's just not say sine squared theta because the variable is t here. Cos squared t plus sine squared t is equal to 1. So x squared plus y squared over 4 is equal to 1, and that is again an ellipse. That's again an ellipse. Next we have x equals 5 cos theta, y is equal to 5 sine theta. What kind of equation do we have now? I can say x over 5 is equal to cos theta, y over 5 is equal to sine theta. Now again I'm going to use the Pythagorean identity. Sine squared theta plus cos squared theta is equal to 1. X over 5 square plus y over 5 square equals 1. X squared over 25 plus y squared over 25 is 1. I can say from here x squared plus y squared equals 25, which is a circle with the radius 5. So you can go ahead and plot this. It's going to be a circle with the radius 5 moving in this direction with the arrows 5, negative 5, 5, and negative 5. Okay, now we're going to talk about the derivative and concavity, first derivative and the second derivative. So we're going to be looking at equations to the tangent lines, first derivative and the second derivative of parametric equations. So remember, if a smooth curve C is given by the equation x equals f of t, y equals g of t, then the slope of C, which is the slope of the tangent line, at the point xy is dy dx, which is dy dt over dx dt, as long as dx dt is not equal to 0. Differentiation in parametric form. So if we want to find the dy dx here, we want to find the derivative here, we know x and y in the parametric form. So how do we find the derivative here when we know x and y in the parametric form? We're going to go ahead and use the formula dy dx is equal to dy dt over dx dt. Dy dt over dx dt, that's going to give us dy of dx. Okay, so let's go ahead and find dy dt. Dy dt would be negative sine t dx dt would be cosine t. Okay, so from here we can say dy dx is going to equal negative sine t over cosine t, which turns out to be negative tangent t, and that is the derivative. So that's the slope of the tangent line to this curve, which is represented by x equals sine t and y equals cosine t. Now let's talk about the second derivative. Because dy dx is a function of t, we can use the theorem repeatedly to find the higher derivative. So second derivative d square y dx square would be d dx of dy dx, which is going to be d dt, derivative with respect to t of dy dx, over dx dt. Keep that in mind. So derivative in the numerator, we would have derivative with respect to t of dy dx over dx dt. Okay. Same way we can do the third derivative. Okay, d dt of the second derivative is derivative with respect to t over dx dt. Here we have find the equation of tangent line, the example to the parametric equation. We're given x equals t to the fifth minus 4t to the third, y equals t squared, and we're looking at the point 0, 4. Okay, so to find, we want to find the slope tangent line. We want to find the tangent line. So we want to find the equation of tangent line. We are given the point x1, y1, which is 0, 4. Now let's go ahead and eliminate the, either we can eliminate the we don't need to eliminate the parameter. We can just go ahead and use this formula that we just learned here. dy dx equals dy dt over dx dt. So dy dx equals dy dt. Let me not use the dy dt divided by dx dt. Okay, so dy dt is 2t and dx dt is 5t to the fourth minus 12t squared. So from here I can say dy dx equals dy dt 2t divided by 5t to the fourth minus 12t squared. Okay, that is going to be our derivative in this case. So we need to figure out when x is 0, what is the value of t? When y is 4, what's the value of t? Either equation can be used to find out the corresponding value of t. So when y is 4, what is t going to equal? Y is 4, t squared gives me y. So square of t is equal to y is 4, that means t is equal to 2. So we need to find the derivative that we just found when t is equal to 2. And we could figure that t is equal to 2 either from the x part of the equation or from the y part of the equation. We could plug x as 0 and then solve for t. dy dx when t is 2. dy dx when t is equal to 2, that is going to be dy dx when t is 2 is going to be 2 times 2 over 5 times 2 to the fourth power minus 12 times 2 to the second power. Let's see, what does that turn out to be? Using a calculator, that's going to be negative 1/8. That is my slope of the tangent line. Once we know the slope of the tangent line, it's not difficult to write equation of tangent line. Always label what you're writing. Equation of tangent line. Equation of tangent line would be y minus y1 is equal to mx minus x1. y1 is 4, m we just found the slope, x1 is 0. And here's my equation of tangent line. See another example, finding the slope and concavity. So now we're looking for slope of tangent line, but we also want to find out concavity, if the graph is concave up or the graph is concave down. So for that, we have just talked about how to find the second derivative. So we'll be using that to find the second derivative. And let's see. So t is greater than or equal to 0, x equals square root of t, y is equal to 1/4 t squared minus 4. Find the slope and concavity at 2, 3. Because to find the concavity, we need the second derivative. To find the slope of tangent line, we need the first derivative. So let's go ahead and find dy dx is dy dt over dx dt. dy dt is, I'm just going to write x is equal to t to the power 1/2, y is equal to 1/4 t squared minus 1. Okay, And from here, we can say dy dt is 1/4 times 2t, which is going to be 1/2 t. 1/2 t divided by dx dt is going to be, let me write it down. I don't want to miss anything here. So dy dt is 1/4 times 2t, which is t over 2. Dx dt is 1/2 square root of t. Okay, so we have t over 2 divided by 1/2 square root of t, which turns out to be t over 2 times 2 square root of t, which 2 and 2 cancels. Square root of t is t to the power 1/2, 1/2 plus 1, t to the power 3/2. That's what we are left with, t to the power 3/2. So now this is going to give me the slope of tangent line, but I do have a mystery piece. I need to find out when x is 2, what is the t equal to? When x is 2, what is t equal to? We can clearly see, because square root of t is equal to x, when x is 2, t is going to be 4. When x is 2, t is equal to 4. So we can find dy dx, slope of the tangent line, when x is equal to 2, is going to give me, I'm going to plug the 4 for the t into the formula we just found, into the derivative that we just found. Square root of 4 to the third power, square root of 4 is 2, 2 to the third power is 8. So we get that 8 is the slope of the tangent line. Slope of tangent line is 8. Slope of tangent line is the 8. Now we also want to find out concavity. So to find concavity, we need to find the second derivative. We already found the first derivative, but we're going to be looking at the second derivative now. So let's go ahead and find the second derivative. I'm going to erase the work for, make some space to find the second derivative. So the second derivative, keep in mind, second derivative, d square y dx square, is second derivative is derivative with respect to t of dy dx divided by dx dt. Derivative with respect to t of dy dx divided by dx dt. Okay, so derivative with respect to t of dy dx. We just found the dy dx, which is equal to t to the power 3/2. So what is that going to be? That's going to be 3/2. T to the power 3/2 minus 1 is 1/2. Over dx dt, we just found dx dt is 1/2 square root of t. Let's go ahead and simplify, and that turns out to be 3t. So when t is 4, we get, when t is 4, second derivative is equal to 12, which is greater than 0. So if my second derivative is greater than 0, then my graph is concave up. My graph is concave up. A curve with two tangent lines at a point. So here we're looking at one curve that has two different tangent lines. It's a parametric equation, and we're looking for the tangent line at positive pi over 2 and negative pi over 2. The curve is given, defined by x equals 2t minus pi sine t, y equals 2 minus pi cosine t. And we're looking for the point 0, 2 on the rectangular coordinate system xy. Okay, so to find the equation of tangent line, first thing we need is the slope of the tangent line. So x is equal to 2t minus pi sine t. Dx dt is going to equal, so let's see, dx dt is going to be, that would be 2 minus pi cosine t. Let's also find dy dt. Dy dt is going to be positive pi, because the derivative of cosine is negative, pi sine t. Pi sine t. Okay, now we can find the derivative, but before that, we also need to think about when x is 0, what is t going to equal? When x is 0, what is t? We can either solve it from the x function or the y function. So when x is 0, what is t going to equal? So let's go ahead and plug 0 is equal to 2t minus pi sine t. 2t minus pi sine t, which gives me 2t, this was a 0 here, 2t is equal to pi sine t. 2t over pi is equal to sine t. 2t over pi is equal to sine t. So when 2t over pi is equal to sine t, this gives me either t is equal to 0. We also need to do from the y side here. When y is 2, we have 2 minus 2 is equal to 2 minus pi cosine t. 2 minus 2 is 0. I have negative pi cosine t. So cosine t is equal to 0. Cosine is the x value. When is the x value going to be 0? The x value is going to be 0 when I'm at plus minus pi over 2. And same thing here, 2t is equal to pi sine t when t is equal to plus minus pi over 2. T is equal to plus minus pi over 2. Okay. All right, so now we are going to be able to find our derivative here, slope of the tangent line, by doing dy dx equals dy dt divided by dx dt. And we'll be able to plug in the value of t to evaluate the derivative. Dy dt is pi sine t over 2 minus pi cosine t. So we're going to plug the t equals positive pi over 2 to make more space for myself here. Okay, let's find dy dx when t is equal to positive pi over 2. That would be t sine pi sine pi over 2, 2 minus pi cosine pi over 2. Using a calculator, that would turn out to be equal to pi over 2. Dy dx when t is negative pi over 2, that's going to turn out to be pi sine negative pi over 2. That's going to pull out the negative in the front. For the cosine negative pi over 2, it's going to be the same value. So it's negative pi over 2. Once we have our slopes of the tangent lines, we are ready to write equation of the tangent line. Equation of tangent lines will be, we'll have two equations here. Equations of tangent lines. Equation of tangent line would be y minus y1, which is y minus 2 is equal to m, x minus x1, x minus 0. So that's at t is equal to pi over 2, and then at t is equal to negative pi over 2 at the slope m. That's not the value of t, this is the slope m. So at the point this is going to be line at point 02. At point 02 we have two tangents, one with the positive slope, one with the negative slope. It's not at t equal to something, it's at point 02. And at that point, t has two values, positive pi over 2 and the negative pi over 2. Okay, now for the arc length for parametric equations, the formula is going to be, we're going to go from our rectangular coordinates. The formula was a to b square root of 1 plus f prime of x squared. Now we're going to replace dy dx with the formula we just did for parametric equation derivative, and it's going to turn out to be, this is going to be the formula for arc length in parametric equations, and for surface area we'll have this formula again deriving from the arc length formula.